Okay, now what happens if there are multiple options for Lewis dot structures? And that's where what are called resonance structures are going to come in. A resonance structure is like different possible ways to connect them. Mainly it's if you have a double or triple bond, and it's like, well, you could have the double bond over here, or you could have the double bond over here. Those are resonance structures. Okay. Ozone is a perfect example of this. Ozone is O3. And if you draw it following all of our rules, your molecule looks like this. Okay, got an octet on everything. I have one double bond, because if I made two double bonds, then I would have either not enough electrons, or, excuse me, I would have more than an octet. So I only need one, but I can either draw the double bond over here, or I can draw the double bond over here. Now you might be like, well, that's the exact same molecule, just flipped. Well, yes, it is. But technically, if these were different oxygens, this bond could be either here or here. So it's called a resonance structure when you can move the double or triple bonds. And the way that we represent those then is we put a double-headed arrow between them that shows it's either this or this, and those are resonance structures. Okay, so another example over here is the carbonate ion, CO3 2-. Carbon in the middle, oxygens on the outside. Okay, to make everything have an octet, I only need one double bond. I don't need three. That would mess everything up. So technically, the double bond can be on this bond, or on this bond. So I draw it all three ways, and I put a double-headed arrow between each one. That's how you show a resonance structure. So in example number 6, I want you to show all the resonance structures for SO2 and C6H6. C6H6 is a little hard, but I do want you to try at least to do SO2 and then check your answer. So go ahead and pause it and do it. Okay, SO2 is going to look like this. I drew my Lewis dot structure. I only had 18 valence electrons, so it should look like this. Everything has an octet. I don't need to make two double bonds because that's going to screw everything up. So it could be either here or here. This one I kind of need to tell you that all of the carbons should be connected in a circle. And if you connect all the carbons in a circle and you put all the hydrogens on the outside, then you need 3 double bonds, and you can't have them next to each other because that breaks the octet rule. So they are separated out. So it can either look like this, or it can look like this. So these are the resonance structures of what's called benzene. This is a really organic molecule and something that we would talk about in Chem 162. Now, sometimes different resonance structures can be better than others. So how do we determine which resonance structure is the best, or which one is more stable? Because they are different, and that is true. If one is more stable, then most of the time you'll find molecules with that resonance structure. So we assign what are called formal charges. So what are they? They are fictitious charges. Literally, we made them up, but they help us in determining what theoretically and in actuality are the better structures. So they're fictitious charges that we assign to each atom in a molecule. And like I said, it tells us the best resonance structure. So how do you calculate the formal charges of something? It's actually very easy to calculate formal charges. And what you do is you take the valence electrons for that atom. So like how many electrons it has regarding the periodic table. So like carbon has 4 valence electrons, right? Okay, so you do that minus the number of bonds and minus the number of dots that are around it. Okay, so bonds, like all the bonds, and double bond would be 2, and then you subtract the dots. So it's valence electrons minus bonds minus dots, and that's your formal charge. Okay, now the general rules for deciding which one is best, okay, is the sum of all the formal charges have to equal to 0, or if whatever the charge of a molecule is. And that will happen if you calculate them correctly. So this is just kind of a check for you. Now, which one is best? The smaller formal charges are preferred. You do not want large formal charges. 0 is the best formal charge. That means that that atom is happy. It's got the number of bonds at once. It has the number of electrons at once. It's good. All right. So the small is the best. 0 is the best. And then the next best would be like +1 or -1, and then +2 or -2. You really don't want to have big formal charges. Okay, that's a really unstable atom. If your formal charges can't all be 0, so like if you have one where all the formal charges are 0, that's the best structure. However, if they aren't all 0, okay, so like if your formal charges cannot all be 0, then the negative formal charges should go on your most electronegative atom, because those are the ones that like to have the electrons. Okay, so you want to shoot for all 0s. But if you're looking at 3 structures and you're like, well, there's no way to have all of the atoms be 0, whichever one has the least formal charges and the negative on the most electronegative atom, so the one furthest up and to the right, that's the best structure. So let's do it for HCN. Is the structure HCN or HNC? Like, which one is better? So go ahead and draw those. Try to follow your Lewis dot structures, and then we'll do formal charges. Okay, so these are the two Lewis dot structures. If you follow all of the rules to get everything in octet, hydrogen cannot double or triple bond, and it only wants two, so this is good and this is good. Like, okay, let's assign our formal charges. So you do the number of valence electrons that it has from the periodic table. So hydrogen, for example, has 1, it's in column 1, minus the number of bonds, well, it has 1 bond, and minus the number of dots, well, it has no dots. So it's just 1 minus 1. So hydrogen is 0. Let's see if I can get this pen to work again. Okay, so hydrogen is 0. Carbon has 4 valence electrons, so you do 4 minus the number of bonds. I have 1, 2, 3, 4, and the number of dots 0, so carbon is also 0. Nitrogen is in column 5, so it has 5 valence electrons, so you do 5 minus the number of dots minus the number of bonds, so 5 minus 1, 2, 3, 4, 5 is 0. Well, I can already tell you this one is going to be the best structure because they all have 0 formal charges. So let's check the other one. Okay, so over here, hydrogen again has 1 minus 1 is 0. Nitrogen has 5 minus it has 4 bonds, so it's actually just 1 or plus 1. And then carbon comes with 4, so I would go 4 minus 3 minus 2 is negative 1. So this is the better one because of B. So I would try B here, which Lewis dot structure for cyanate ion is the best. Remember that negative charge means you add an electron. So count some more valence electrons, make it into a structure, and then decide which one is best. Okay, so answer-wise, these are my structures, okay? Notice I put these between them, the resonance structure double-headed arrow. I did put them in brackets because they have a -1 charge. This is a lot of practice here. It could either be, so like what were the options? Well, resonance-wise, I could either have 2 double bonds, or I could have a single and a triple, or I could flip it and do a triple over here and a single over here. Those are the options for moving double or triple bonds. So once I did that, I checked all my formal charges. This one is 0, 0, -1. This was -1, 0, 0. And this one is +1, 0, and -2. Okay, so if you're looking at formal charges wise, this one is definitely not the best answer. Okay, we want as many zeros as possible. These both have 2 zeros and a -1. So then you want to pick the one that has the minus formal charge, that -1, on the most electronegative atom. Well, of the options, I've got nitrogen as an option and oxygen as an option. So I look at the periodic table, oxygen is further up and to the right, so it has a higher electronegativity, so that's where I want my -1. So this structure is the best because the -1 formal charge is on oxygen, which is the most electronegative atom.